So, welcome back students. We are basically discussing the first guideline of classical resolution or stereochemical based strategies, and we said that we have to follow certain instruction in the stereochemical strategies. Our initial point is classical resolution, which basically includes kinetic resolution, dynamic kinetic resolution, parallel kinetic resolution, etc. And we mainly focused on KR and DKR. PKR we have not talked about, it is not basically essential at this point to know detail about the PKR. In classical resolution, there are this method is very powerful, and till today many industry follow this classical resolution method. I will probably try to give you a case studies where classical resolution was done through a technique which is now named as CDA. Now, CDA basically stands for chiral derivatizing agent. It basically means that if you having a racemic mixture, you react with the racemic mixture to a chiral derivatizing agent through a covalent bond formation. Now, this chiral derivatizing agent must be very cheap, commercially available, and it can be easily derivatized, it can be easily reacted, it must be available in enantiomer pure form. So, those are the certain prerequisite you need to maintain, and the final point is it can be recycled. If you can recycle it, that will be also extremely important. So, now what I am saying, I will give you a particular prochiral compound, and I said we initially convert this compound to a racemic mixture. Now, this reaction we have discussed in detail in the earlier lecture. So, please go through it. Now, this compound initially is prochiral, you do a desimmetrization to get racemic mixture, that is fine. Now, what I say? I am saying that now I will be reacting this compound with a chiral derivatizing agent. The chiral derivatizing agent, what was commercially available is this isocyanate. Now, before we talk about this reaction, you need to know how isocyanates react with alcohols. Isocyanates are basically compounds having this structure. So, if you react isocyanate with this alcohol in presence of a very mild base like triethylamine, this alcohol nucleophile attack to this carbonyl. Okay. Then this carbonyl backfire, it gives a these things. So, basically you will now get this is nothing a carbamate, it is called a carbamate derivative, say carbamate derivative. Now, carbamate derivative you can basically clip the corresponding carbamate derivative to get back your original alcohol back. Now, normally you can clip this carbamate. Now, this carbamate is basically ester, you can clip this carbamate through reductive cleavage. Like simple, you react with lithium aluminum hydride to get back your alcohol as it is. So, this is the way you can basically react. Now, what I am saying that if you having a chiral alcohol or racemic alcohol and you have this part here. So, now we will start working on the real problem which was given to us. So, I am saying that you are having this compound as well as you are having this compound, these two are basically enantiomer. So, you are having this plus or see plus, this is minus, two enantiomers. Now, this or you can say R and S. Now, this compound next is reacted with a chiral derivatizing agent which is a chiral isocyanate, chiral isocyanate. The similar way this isocyanate is chiral. So, means let us say it is having a R absolute configuration. So, if both the enantiomers react in the equal fashion, you will get a RR carbamate, you will get a RR carbamate, and you will also get a SR carbamate. Fine. Now, these two compounds are diastereomers. These two compounds are diastereomers. So, you can easily separate them out. Diastereomers having different physical properties, all of us know. So, these two compounds now basically you can easily separate. Now, what you need to do? You basically clip the chiral derivatizing agent. So, now you get pure enantiomer of R and pure enantiomer of S. So, this is the very standard text standard protocol of a physical kinetic resolution. It is not a kinetic resolution in true sense, it is basically a taking the two enantiomers reacting in a similar fashion through a chiral derivatizing agent, And in the kinetic resolution, if you see kinetic resolution, now I try to give you a example. Normally we will not go very detail. We will say in kinetic resolution, if you are having a racemic mixture, say having this particular compound, this and its mirror image. Okay. So, both compounds are there, they are basically mirror image isomer. I am saying their rate has to be substantially differentiated. Now, there are many ways you can we can do the kinetic resolution. Probably the best way people are now using a enzymatic pathway. Now, initially if you follow the kinetic resolution strategy, we said that this enantiomer have similar kind of functional group attachment except the stereo orientation in space. Now, if we create a chiral environment throughout both the enantiomer, like you put some extra groups. So, these groups are basically chiral. Now, the only difference is the groups are chiral around the enantiomer. So, now these enantiomers are basically in diastereomeric environment, means that this enantiomer is having R or S, I am not sure, but just for a simplified thing I am giving you this R, this S. Now, I am saying that this both the enantiomers have been put in a chiral environment. Now, as their stereochemistry differ in the stereogenic center, this chiral environment is similar. So, basically it is like a CDA. So, now they react in a, or they can kind of interact it with this chiral atmosphere. Now, I am saying that in case of CDA both the enantiomer reacts, but here one enantiomer has favorable interaction, one enantiomer has favorable interaction with this chiral environment, favorable interaction with this chiral atmosphere or chiral environment. Now, this favorable interaction makes sure that one of the enantiomer will be reacting in a faster rate compared to the other enantiomer. So, basically enantiomers, both the enantiomers are put in a chiral atmosphere, and then through diastereo selection, it is basically diastereo selection, you are getting the kinetic resolution. The slow reacting enantiomer will not be having a favorable interaction with this chiral environment. Now, this chiral environment basically can be created mainly chiral environment, which is essential for this thing, is mainly created by chiral catalyst or chiral reagent. Now, out of this chiral catalyst, enzymes have been now very effectively used for this kind of resolution, and these resolutions are now termed as EKR or enzymatic kinetic resolution. But definitely we are not going to discuss these things in detail here, because this is beyond of our scope. So, we will try to bypass it. Now, in the case of kinetic resolution, he always says that there is another process which is named as stereo inversion. Now, what is stereo inversion? Stereo inversion means that if you are having a stereo center, if there is a way you can invert the stereo center depending on your need. I am saying your starting material is this, which is easily available. Now, your target molecule is this. So, can you do a simple inversion by a FGI? It is a very classical technique, Probably the best solution is you can simply do a SN2 inversion or a Walden inversion, which was done earlier. It was still followed. Now, let us talk about a similar kind of reaction which probably we have not heard about, or if you know it, still you can have a more information. We are talking about a reaction which basically named as Mitsunobu inversion. It is a named reaction. It is called a modern SN2 reaction. Now, this reaction is very important in terms of if you are having a stereo center, you want to invert the stereo centers, mainly your strategy is basically focused if you are having a alcohol containing stereogenic center. Okay. Now, alcohol containing stereogenic center, the Mitsunobu reaction is very important. Now, what exactly in Mitsunobu reaction was done? Mitsunobu reaction, you basically, I just try to give you a schematic thing. You have a alcohol, you mix the alcohol with triphenyl phosphine and a reagent abbreviated as DATE, N double bond N CO2 AT, and you react with a nucleophile, so that you basically get this compound. This is a one pot reaction, all the components are mixed together and you can get this compound. Now, initially problem associated with this simple one pot substitution by alcohol is very difficult, because we always says that alcohol are bad leaving group, alcohol are very bad leaving group. That is why in the standard textbook of SN2 reaction, we always says that this alcohol are converted to tosylate or mesylate, then you react with a suitable nucleophile. Now, here what we did, we reacted with triphenyl phosphine and a reagent abbreviated as DATE, diethyl azidicarboxylate. Now, what exactly this DATE and triphenyl phosphine does? Now, initially it was this diethyl azidicarboxylate and this triphenyl phosphine basically react. This phosphorus lone pair attacks here and basically give you a negative charge on this nitrogen, which is definitely stabilized by this electron withdrawing of this adjacent CO2 So, this is the initial step which basically happens. Now, we have your substrate as a alcohol as well as you are having this any nucleophile. Now, if your substrate now having a alcohol, say that this can give you the acidic hydrogen to this nitrogen. So, the nitrogen now is basically quenched this negative charge and basically give you N with this triphenyl phosphine and alcohol now become RCH2O minus. It is fine. Now, this RCH2O minus will now react, this is also a good nucleophile, this basically react to this phosphine and now this phosphorus nitrogen bond will now try to cleave and then again it will put a negative charge on this nitrogen which is stabilized through this electron withdrawing and what you will get? You basically get a this species oxygen phosphorus species. Now, oxygen and phosphorus having a very strong bond energy basically it should be right like this OP PH3 plus the very strong bond energy. Now, this N minus is there. Now, what happened? If you are having a nucleophile which basically donates this hydrogen to become a this NH CO2 NH CO2 and it gives you a Nu minus. In addition, you are having a RCH2O P plus PH3. Then this nucleophile attacks through a backside attack of this carbon oxygen bond and gives you a phosphorus oxygen bond. So, phosphorus oxygen bond is much more energetically favorable and then basically you get RCH2Nu plus triphenyl phosphine oxide as a byproduct which is comes as solid. So, in reality you basically get these things and this is your SN2 step which is your Mitsunobu inversion. So, the problem which I am now trying to address, if you have a compound something like this, how you can invert this alcohol. The best way to do is Mitsunobu reaction, you react with triphenyl phosphine, react with date, but what about the nucleophile? You simply cannot take a nucleophile as a water definitely or OH minus, those are they may be a good nucleophile, but OH minus is a harsh condition. So, try to take a nucleophile which may have a tendency to donate its hydrogen also, because if you follow the mechanism you need a hydrogen source to quench this nitrogen. If you take acetic acid or benzoic acid as a nucleophile, initial step basically what will get after the first inversion, you get a acetate here. So, acetate is acting as a nucleophile. Now, you just do a alkaline hydrolysis or you can do a reductive cleavage by lithium aluminum hydride, you get your product here. So, this is absolutely simple and you can basically complete the stereo inversion or stereo mutation process based on this. Next, we will try to do a problem which is exactly based on this. The problem which was next given to you, a bicyclic compound is given. The bicyclic compound is given, the stereochemistry at the stereogenic center was having this structure. Now, this is your target molecule. The starting material which was given to you is this alpha beta unsaturated ketone. Now, from the very beginning it looks simple. If you say that okay, we can do a simple Luce reduction, it can be done, but in reality it is not that simple. If you try to do this or try to draw these compounds conformational behavior in the ground state, you will find that this compound it reality it exists as this kind of structure. So, this kind of structure basically means that this compound is kind of tilted, the hydrogens are below the plane. It basically like this, 2 cyclopentane ring is like this and your hydrogens are below. So, you have this compound. So, now you are trying to do a simple hydride addition, you will see that hydride now its compound is like this and the methyls are top. So, top face is basically blocked, top face is blocked. So, hydride has to come from the bottom face. So, if you now do a simple Luce reduction, you will basically able to get the compound which is not the required compound which was desired. You basically get this compound, right. So, initial hydride addition from the top face is hindered, but the bottom face or the below face is possible, and this is basically due to the structure which I have shown. It is basically kind of this structure. So, makes that as the molecule is kind of folded, the entire top face is blocked. So, now if you do this reaction you get this product, but this is not the target. So, what you now need to do? Now, basically you can use the Matsunobu reaction which will be coming into place. So, now initial your Luce reduction or any sterical, actually in principle Luce probably will not fit here, because Luce is a very gives you a small hydride source. Now, if you can do a reduction with a pretty bulky reagent like Dibal which is having a sterically bulky hydride, in case of Luce probably you get both the diastereomers 1:1, that probably will not serve. Now, if you do a Dibal reduction you get only exclusively this product, but then you need to invert the stereocenter share. Now, in the last part we discussed that we can invert the stereocenter by a stereoinversion process through a Matsunobu reaction. So, what you next do? You do a Matsunobu reaction. The same reagent condition, and then do the hydrolysis, acetate hydrolysis. So, now basically you get your product back, this OH which is the target molecule was drawn. So, Matsunobu reaction, the reagent conditions will be using triphenyl phosphine, you will be using DADE, and you will be using acetic acid as the main reagent. So, these things in combination will give you the initial inverted acetate, then you follow the hydrolysis, that will basically give you the complete story. So, kinetic resolution, dynamic kinetic resolution and stereo mutation, stereo inversion, we basically covered little bit, and few examples have been provided. Now, the next point in the stereochemical strategies, we will now try to cover substrate directed approach. Now, here we will straightforward go to some, I will assign some problem to you. I will say that I will be having this particular compound, from this I want this to target. So, you are having this cyclohexane based compound, and I will be needing this target, target 1 and target 2. The one is epoxide, one is cyclopropane. But if you closely analyze, the stereochemistry of this hydroxy group was the governing factor, means that whatever stereochemistry the hydroxy group is having, the final product has same stereochemical orientation. If it is beta, this is also beta, this is beta, this is beta. So, means that you have to devise some reagent or some reagent system, so that stereochemical information was preserved, or this stereochemical information directs the incoming reagent to attack from this one. Now, first talk about the initial example. Now, for the initial example, if you draw its ground state conformation, is basically a half chair form. In half chair form, the OH is above. So, basically it is pseudo equatorial. Now, this pseudo equatorial basically you can write like this. This is the initial starting material. Now, see, the starting material is having a pi bond, where two faces are available, the top face or the beta face, and the bottom face is the alpha face. Okay. This is done. Now, the reagent, I am saying that you use a reagent MCPBA, which is very known epoxidizing agent or electron deficient epoxidizing agent. Now, MCPBA, I will now draw the structure. I will put AR. AR is your basically this aromatic things is basically metachloro. So, you now put AR C double bond O. You are having this oxygen, another oxygen, and then H. Now, what happened? This pseudo equatorial or the beta phase OH will try to have a hydrogen bonding with this electron deficient oxygen of this metachloroperbenzoic acid. It could have a intramolecular hydrogen something like this. So, the whole reagent system will basically through this intramolecular hydrogen bonding, it will try to approach from the top face. As this OH is pseudo equatorial, it is not pseudo axial. If it has to be pseudo axial, the MCPBA will coming from this bottom face. So, this was the now your epoxidation will take part from this bottom face, and you will find that product distribution which was given here, you will basically get the, this is as a major product, this is as a major product or main product. Now, if you have this compound like this epoxide, sorry, this alcohol, then you do MCPBA, the same analogy you will get the alpha epoxide, get the alpha epoxide, you get the alpha epoxide. So, depending on the substrate stereochemistry, you can basically control the epoxidation reaction. The second case, you are having a similar kind of system where basically you do a Simon-Smith reaction, you have to do it. The Simon-Smith reaction, we say the reagent system is CH2I2 and you react with a zinc. It basically will give you a zinc carbenoid species whose structure is ICH2 ZnI, this carbenoid. Now, initially this carbenoid reacts with this alcohol which was a starting material. It basically gives you this kind of OZn CH2I. Now, this intermediate you can basically again write it in the similar pseudo equatorial way, your O, your Zn, then basically you are having this your CH2 and then you are having this iodo which is also having a zinc coordination. So, now the beta phase is more accessible, the alpha phase is not, accessible. So, in this case also if you trying to do this reaction, you will basically get this OH and this CH2. So, this is the induction was pretty good. The advantage is you are not using any chiral reagents or the chiral catalyst. Your substrate is having pre-existing chiral center, in the substrate. That basically dictates the whole thing, and then this kind of substrate directed stereo control is absolutely important. You will find many examples, and particularly for cyclic substrate the control is absolutely good, because cyclic substrate has this well defined conformational behavior. We will keep on continuing this discussion in the next lecture. Till then, have a good time and goodbye.